So the governing principle behind what we're going to be looking at today is the principle of the lever. All right. So here's the big idea. Suppose we put two masses on a board as pictured below. So you can think of this as like a seesaw. Like, back when I was a kid, we had seesaws sitting on either side. And we put a fulcrum. So the fulcrum is this triangle thing. And the goal is we want to position the fulcrum so that things are completely balanced. All right. So putting the mass times distance is called a moment. Moment is mass times distance. All right. And so the principle of the lever states that in order for this to be balanced, the moment here from M1 has to equal the moment from M2. So the moment from M1 would be M1 D1, and that's got to be the moment for the other mass, M2 D2. And that's the principle of the lever. So this goes back to like Archimedes. Archimedes had a quote, "Give me a lever arm long enough and I'll be able to lift the world." Okay. So to help us find where we want to put the fulcrum, we imagine that the fulcrum is going to get positioned at some value x bar. Now notice we're using the bar here. X bar is going to be a weighted kind of average. So normally we use the bar notation to denote an average. So this is going to be a weighted average here. Okay, so we can work through the algebra to figure this out. M1 D1 has to be the same as M2 D2. All right. So once again, this is D1 here, and this is D2 here. Okay. Now what is D1? D1 would be x minus x bar minus x1, and then D2 would be x2 minus x bar. These absolute values are here for the more general case where you don't know who's on the left and who's on the right. So you distribute through. Get everything with the x bar on one side, so you can factor it out. And then boom, you get down to here. And so if you look at what the x bar is actually equal to, x bar is m1 x1 plus m2 x2 over m1 plus m2. So the numerator here is the total moment of the system, and this is the total mass of the system. So the total moment here, we call that capital M. The total mass, we call that little m. Now this total moment, if we think about what's actually here, if we think of the origin being here, then the m1 x1 plus the m2 x2, this is the total moment about the origin. Okay? It's the total moment about the origin. So the way to get the x bar here is called the center of mass. And once again, you can think of that's the total moment about the origin over the total mass. So it literally is like a weighted average like you would see in statistics, okay? And spoiler alert, all the stuff we're going to do today with moments and first moments and second moments have statistical analogs later on, okay? So some folks, when they get to Calc 3, they'll do the engineering kind of stuff like we're doing today. Some people will do the statistics kind of stuff. It's all the same. It's all the same mathematics, just different interpretations. So suppose we go from 2 masses to having n masses. So if we have n masses on this teeter-totter, and they each have mass, say m1, m2, m3, say up to m sub n, and they're at locations x1, x2, x3, all up to x sub n. Then the total mass, little m, to get the total mass, well, you just add up all the masses. And to get the total moment, you would just add up all the moments. So that's the key idea here. And we've seen this before, is that mass and moments are additive. And you know that if we have things that are additive, that means that there's a good chance we'll be able to use an integral to calculate the mass and the moments for more complicated systems. So that's your total mass. And then that would be the sigma notation for your total moment. And then, of course, to get your x bar, your center of mass, you take the total moment divided by the total mass. And what that center of mass is, so let's say you work through the calculations, and let's say your x bar is here. Let's say that's where it works out to be. What's the point of finding the center of mass of this system? Well, basically you can, as far as physics is concerned, if you're taking this system and moving it, and you're trying to calculate its kinetic energy and stuff like that, this entire system would be equivalent to all of the mass m at that point. So when we talked about work a couple days ago, and we were doing an example of launching a satellite off the surface of the Earth, I made the comment that we assume that all of the mass of the Earth is concentrated at its center. Well, it's at its center of mass. It's at a center of gravity in there. Okay. And so in physics, if you have masses spread out, you typically calculate the center of mass, and then you can just boil everything down to that one point moving with that one mass. Okay. So that's why they care about these sorts of things. It's the perfect balancing point. Okay. So something usually we would do, and if we were meeting face to face, is we'd have a bunch of rulers, and then we'd have like stacks of coins, right? We'd have like, a stack of 5 pennies, a stack of 2 pennies, and we'd figure out the center of mass, and then we would see that wherever the center of mass is where we would put our pencil to balance the ruler with those two stacks of pennies or 3 stacks of pennies, however many we have. Okay. So there's some good experimentation you can do with this. So let's work through one of these examples to make sure we understand how this works. Suppose we have 3 masses. M1 is 10 at -3, M2 is 5 at 1, and M3 is 2 at 4. So here's our 0. We've got 1, 2, -3, and we got a mass of 10 there. At 1, we got a mass of 5, and at 2, we got a mass at, at 4, we got a mass of 2. All right, so to get the center of mass, we need the total moment divided by the total mass. The total mass we're going to get by adding up the masses. So that's 17. The total moment we get by adding up all the moments. And how do we get the moments? We take these moments are moments about 0 So we take the mass, in this case 10, times the displacement from 0, -3, plus the mass of 5 times its displacement from 0, which is 1, plus the mass of 2 times its displacement from 0, 4. So this is m1x1 plus m2x2 plus m3x3. And this is just m1 plus m2 plus m3. Now if you go through the calculations here, you get a -30 plus 5 is -25 plus 8 is a -17. And so the x bar here, total moment over total mass, -17 over 17 is -1. So that means that so that's my x bar. That means that if I put a fulcrum here, that this would perfectly balance. This means that for some of the physics applications, like straight line motion, kinetic energy, that this system can be replaced conceptually with the system of 17 pounds, or 17 mass, whatever, 17 whatever, with a mass of 17 at the x value -1. Okay, so that's what that center of mass means. You take that whole system, put it there. That's the balancing point. So this is how you do this kind of thing using what we call a discrete system. Discrete system is you have a finite number of masses spread out on the x-axis. So what's a continuous system? A continuous system would be something like if you had a wire and you had the density of the wire, and maybe the wire was heavier at one end than the other, so maybe the density changes. So let's talk about continuous systems. Suppose we model a wire as an interval AB and let rho of x be the linear density of the wire. This means that rho of x tells you the density of the wire with units of mass per length at location x. So we're thinking of a wire We're thinking of the wire being modeled by an interval from A to B. And rho of x, so that's our Greek letter rho, this has units of mass per length. So maybe the wire is made out of a composite material. It's denser on one end than the other. And so what if we wanted to figure out the mass of the wire? Well, how would we do that? Well, we know that mass is additive. So what we could do is we could go into the interval here and chop it up into little pieces. And let's look at the mass of the ith piece. So let's let m sub I be the mass of the ith piece. So the way I get the mass of the ith piece is I'd have to take the density times the length. All right, so just rearranging this formula here. Density times the length. So, what's the length of each of these little subintervals? Well, the length is going to be delta xi. So that's going to be the density times my delta xi. And here's where we're going to have to do approximations. since we're assuming that the function, the density, is continuous, remember what continuous means. Continuous means if the inputs are close, then the outputs are close. So if I'm chopping this wire up into really, really small pieces, the density at one end of the wire, of that small piece of wire is going to be roughly the same as the density anywhere else in that wire. So I'm going to make an approximation and say this is rho of x sub I delta x sub I. And so once again, that's where continuity comes into play. So my total mass m would be the sum, I goes from 1 to n, of m sub i's. Right? I'm trying to find the mass of a wire. If I cut the wire up into 117 pieces, I could just weigh each of those, or find the mass of those 117 pieces and add it together and get the total mass. And we're approximating the mass of the ith piece by looking at the density at the one endpoint times the delta xi. Okay, so if we're on the ith piece here, x sub I minus 1 to x sub I, it's got a length of delta x sub I. We're using the density here at the right endpoint to approximate the density everywhere. Oops. And now we do what we always do. We've chopped it up. We've made approximations. And now to get a better approximation, we chop it up into smaller and smaller and smaller pieces. So we let the norms of the partition go to 0, smaller and smaller pieces. What's going to pop out, folks? The summation turns into an integral. We're chopping up the interval from a to b. The function I'm sampling is rho of x, and the delta x there becomes the dx. And so once again, hopefully you can read the integral here. This is your density at the point x, and this is your infinitesimal length. Which means that when you take that density times that length, this is giving you the mass, and this is adding up all the mass to get to the total mass. Make sense? Now, to get the total moment, you do the same kind of thing. Moments are additive. So if you take this wire from A to B and chop it up into these pieces, and you're trying to find the moment, well, looking at this each piece from x sub I minus 1 to x sub I, so we'll let m sub I be the moment about the origin of the ith piece. And we know that that's the mass of the ith piece times the displacement of the origin. Now, we know that the mass of the ith piece we can approximate by rho of xi delta xi, because once again, we're assuming that delta xi is small, and eventually it's going to go to 0, get smaller and smaller and smaller. And so the density, once again, at the right endpoint is more or less the density of the entire subinterval there. And now we're also going to approximate the displacement. How far away is this piece from the origin? Well, if it's really, really small, then you could pick the left endpoint, the right endpoint, some point in between. Because if the delta x sub I is really small, all of these points are more or less the same. So we'll approximate that by x sub I. So we actually have two approximations going into that. So the total moment would be the sum of these individual moments. And I'm going to write the delta xi on the other side. I'll move the xi up to the front. And then we do what we always do. We let the norm of the partitions go to 0. That's like the magic word. That's like the presto here in Calc 2. The summation is going to turn into an integral. So we're taking a discrete sum, making it a continuous sum. We're chopping up the interval from a to b. The function here we're sampling is x times rho of x. And the infinitesimal version of delta x is the dx. And so hopefully, once again, you can read the integral here, is that this is your displacement from the origin. That's your density. And that's your infinitesimal length. So we're getting units of mass times length, and this adds them all up. Okay? That's your total moment. So that's where these formulas come from. And at this stage in the game, and then you get your x bar the same way you did before. Okay? Now, we're not going to work through the details of these examples. This is a handout I use in Calc 3. But we can at least set the integrals up. So if we want to define the center of mass, we would integrate from 0 to 1 the density, e to the minus x dx. That would give us the mass. And then to get the moment, we would integrate from 0 to 1 x, e to the minus x dx. That would give us the moment. And notice, look at what you would have to use to integrate this one. There's integration by parts. Okay, so all of that stuff we did, integration techniques. If you go into Calc 3, you're gonna see all that again. Okay, there's a lot of integration in Calc 3. And then to get your x bar, you would take whatever number you got, m divided by, for the moment, divided by the mass. And since the e is involved, you get goofy looking things, but that ends up being your center of mass. Okay. Now let's generalize that. What if your wire was modeled by y equals f of x, where f is smooth? Remember, that means that f prime of x is continuous. So what if you take your wire and you're not modeling your wire by an interval, but what if you're modeling it by some one of these rectifiable curves here? And let's say you had your density rho here as a function of x, as usual, and that's continuous. The question is, how could we find the mass? Well, what would we do? Well, it's what we always do. We would chop up the inputs here. The old chop and add technique. So if we let m sub I be the mass of the ith piece, well, the mass of the ith piece here is a portion of the curve, so that's an arc length. So this would be the arc length of the ith piece times the density. So there's arc length. Now this is something we did at the end of last week. That would be our delta S sub I. Not delta X, but delta S, change in arc length, times our density, rho of X. So we know how this works. M sub I is going to be approximately equal to, well, we know the arc length differential. That's the square root of 1 plus f prime of x squared. So we'll sample the derivative there at x sub I, because if, once again, the pieces are small enough, then the derivative at x sub I is going to be roughly the derivative at x sub I minus 1. So once again, let's make sure we sketch this out and understand what we're looking at here. That's roughly going to be this. So this is our approximation for our arc length change. And then we'll approximate the density here as we did before. And so the total mass then would be the sum of all these little masses, which is approximately equal to, and we'll put the rho of xi first to make sure it's outside the radical. And now we do what we always do. Take the limit as the norm of the partitions go to 0. The summation is going to turn into an integral. We chop the interval a to b up. The function I'm sampling is rho of x times the square root of 1 plus f prime of x squared dx. And that would be our mass. That would be our mass. Now, if we wanted to get to a moment, well, since this thing lives in the plane in 2 space, there's a moment about each of the axes. The moment about the x-axis and the moment about the y-axis. And that's what we're going to talk about next. We haven't talked about 2-dimensional moments yet, but that would be the mass. Or the way I like to think about it is this is the integral over the curve, if we give the curve the name C. We'll just call that curve C, of rho of x ds. I'll just put rho ds. And once again, that's your density. That's your mass per length times your length. And this is sort of the poster child for what's called a line integral in Calc 3. So once again, if you're moving into Calc 3 or you have to take a class on vector calculus, this is kind of what starts the whole thing off. Okay, this is what starts the whole thing off. All right, so I mentioned 2-dimensional systems, so let's talk about 2-dimensional systems. Suppose now, instead of putting points on a seesaw, suppose we're putting points on like a 2-dimensional plate. We're putting masses on there, and we want to balance. Okay. Well, one of the big principles is that, you know, if you've ever tried to balance a plate, you can kind of find where the plate stops tipping in one direction in the x direction, and then how it stops tipping in the other direction. If you can get it balanced in those two primary directions, then you have the plate balanced. So we know what masses are. We know how to find total mass. How do we find moments? Well, we have two moments. We've got the moment about the x-axis. So the moment about the x-axis is the product of the mass with the displacement from the x-axis. So looking at how far, or the signed value, so displacement is above or below, plus or minus. The displacement here is given by the y value. All right, so the moment about the x-axis is the mass times the y value. The moment about the y-axis is like the moment we had before. So if you think about when we were doing our moments here about 0, we took m1 x1 because that was the displacement to the origin. Well, remember that's where the y-axis would intersect. Okay. So it is just a generalization of what we did before. Now, of course, if you have more than one mass, then you would find each of the moments and add them up because moments are additive. So in general, if you have n masses at these n different points, you find the total mass m by adding up all the little masses. You find the total moment about the x-axis by adding up all the individual moments about the x-axis, and the moment about the y-axis, and the total moment about the y-axis. Now for the center of mass, the x-bar is equal to the moment about the y-axis over the mass, and the y-bar is the moment about the x-axis over the mass. And a lot of students think that the notation kind of has it reversed, right? Well, why is that? Well, if you look at the moment about the y-axis, you're literally looking at how far left and right you are. So when you take the moment about the y-axis divided by the mass, m, that gives you the x-coordinate so that it'll balance left and right. The moment about the x-axis is literally trying to figure out how far up and down you go so it stops tilting across the x-axis. Okay, so it's a little flip, but hopefully it's okay. Notice that the moment about the x-axis involves the y values. The moment about the x-axis involves the x values. So that's really why they're kind of flipped from the get-go. So once again, a quick example to make sure we see how all this works. You've got the same mass as we had before. We've got a mass of 10, 5, and 2, so the total mass there is 17. If we want the moment about the x-axis, we take each of the masses times the displacement to the x-axis, which is the y value. So we would take 10 times the y value. And then we would take 5 times the y value. And then we would take 2 times the y value. So you'd get 28 minus 10. Wait, no. No, not 28. 20 plus 15 is 35 minus 10. So that'd be your total moment would be 25 about the x-axis. Now for the moment about the y-axis, you take each of the mass times the displacement to the y-axis, which is given by the x-coordinate. So you take 10 times the x-coordinate there, negative 3, plus 5 times the x-coordinate 1, plus 2 times the x-coordinate 4, and that's the same 17 we had before, or negative 17 we had before. So the x-coordinate of the center of mass is going to tell you how far left and right you go to keep it from tilting that way. So that's going to be your moment about the y-axis over the mass. That's the -1. And my y-bar would be your 25/17. And so there's our, okay. The moment about the x-axis is positive. That means it has a tendency to be heavy above the x-axis, so we're going to have to move up the y-axis to keep it from tilting that way. The moment about the y-axis is negative. That means it's heavier on the left side, so we have to move a little bit to the left to keep that from tilting. So hopefully that makes sense. Continuous systems. So this is where Calculus 3 shines, is doing this kind of thing. Because what happens in Calculus 3 is x and y become independent variables, and they're both feed into a variable z. And so you don't need to worry about chopping up the x-axis and giving everything in terms of a function of x. You can chop up the x-axis and you can chop up the y-axis. You can integrate in the x direction and then the y direction. Okay? We're not here yet. So we're going to have to go back and just stick with what we know with a single function. And suppose now we have a region bounded by two curves. Y equals f of x and y equals g of x. This should take us right back to what we talked about. We did area between curves. And suppose we have a density function, rho of x, and of course we're going to assume this is continuous. We're going to assume these are continuous as well. Right? Everything's continuous. What if I wanted to find the mass of the region R? Now once again, we're in Calc 1, or excuse me, Calc 2 rather. We're in one-dimensional calculus, we'll say. How are we going to do it? Well, what we'd have to do is we're only allowed to chop up the x-axis. Now, if we chop up the x-axis, what do we get? We get rectangles. All right, so we get this rectangle. Or I should say more generally, if we don't do any approximations, we get these strips. So I'm going to let m sub I be the mass of the ith strip. And what I'm going to do is we're going to approximate the ith strip using a rectangle. So if the ith strip looks like this, I'm going to approximate that using a rectangle. Now, for this density to make sense, the units here must be mass per what? It must be mass per area. Okay? So the mass of the ith strip is going to be the density times the area. And here's where our approximations are going to come in. Once again, we're going to assume that delta x is small. Here's x sub I minus 1. Here's x sub I. We're going to assume that my delta x sub I is small. The function, density function is continuous. Close inputs, close outputs. Rho of xi times the area of this strip. Well, we know what the area of this strip is approximately going to be, and the area of that rectangle. So the area of that rectangle is the height times the width. The height would be f of xi minus g of xi times delta xi. Top of the rectangle is f of xi, bottom of the rectangle is g of xi. And if this looks familiar, it should, because this is what we looked at the beginning of last week. So that means that the total mass, which will be the sum of the mass of each of these strips, is approximately equal to the sum I goes from 1 to n, the density, rho of xi, which is an approximation of the density for all the points in the strip, times the height, which once again, this is an approximation as well. That's another approximation, delta xi. And so as the norm of the partitions run off to 0, and we get skinnier and skinnier strips, the areas of those strips are going to mimic the areas of those rectangles. I'm chopping up the interval from a to b. My discrete sum of sigma turns into a continuous sum integral. What am I integrating? Rho of x, f of x minus g of x dx. That's how we would calculate the mass of that region. What about moments? Well, let's do the moment about the y-axis first, because that's the easier of the two to understand. The first thing we have to talk about, whoops, is the rectangle here. Okay. The center of mass of a rectangle, assuming a constant density, oops, let me do this again. Let me just start over. I'm getting ahead of myself. We need to look at a rectangle here. We're going to assume a constant density. For example, a sheet of paper. All right, 8.5 by 11 sheet of paper, constant density. Where's the center of mass of that rectangle? If I ask you to balance a piece of paper on the tip of your pencil, what would you do? You would literally find the center. And how would I find the center of the piece of paper? Well, you'd probably fold it in half one way, and then fold it in half the other way, and you look where the two lines intersect. So that's halfway over and halfway up. So if I call this x sub I minus 1, and I call that x sub I, then the midpoint, I'll call that x sub I star, would be the average of x sub I minus 1 and x sub I. If the bottom here is g of x sub I and the top is f of x sub I, then the y sub I star, which would be the center here, I'm not labeling things very well. Well, gosh, I hate to introduce new notation here. Let's keep it this way. Let's keep with the tradition. Xi bar, yi bar. How's that? That would be 1/2 f of x sub I plus g of x sub I. Let's do that. So assuming a constant density, the center of mass of the rectangle is going to be the center of the rectangle, halfway over, halfway up. So xi bar, you take the average of the x's, yi bar, you take the average of the y's. Hopefully that makes sense. Just think of taking your piece of paper, folding it one way, then folding it the other way. To balance it, you would look where those two lines intersect. So when we go talk about this now, with this region we've got, with your y equal f of x and your y equal g of x, and we're looking at this representative rectangle here, which is going to represent our slice. And we've got that point there, x sub I bar, y sub I bar. If I wanted the, I'm going to let m sub I be the moment. Oops. M sub yi is going to be the moment of the ith slice about the y-axis. Okay? And so how do I get the moment about the y-axis? Well, I would need the mass of the ith slice times the displacement from the y-axis. Now the displacement from the y-axis, if I had taken the time to label, here we go. The displacement from the y-axis, remember, is given by the x-coordinate. So the mass of the ith slice is approximately equal to what? Well, we did that already. That was rho of x sub I times f of x sub I minus g of x sub I delta x sub I. So that was the approximate mass. That's what we did just a couple minutes ago. You take the density times the area. The displacement from the y-axis, well, since delta x is small, and we're assuming the density there is constant. It's pretty much all going to be the same as the density at x sub I. We're in the situation we just talked about here. And therefore, all of the mass is concentrated at the point x bar I, y bar I. So to find the displacement from here from the y-axis, it's the displacement of the center of mass to the y-axis, which is x sub I bar. So this is the displacement of the center of mass of that rectangle. So the moment about the y-axis, it's the mass of the ith slice times the displacement from the y-axis. To get the mass, we take the density times the area. Assuming we've chopped it up into very thin slices, the density of that slice is going to be constant. We'll call it rho of x sub I. That'll approximate the density for that entire subinterval. The area, we take the height of the rectangle times the width of the rectangle. The displacement, and this is the key, the displacement for the moment, we can assume that all of the mass is at the center of the rectangle. The center of the rectangle is xi bar units away. All right, so there's a good amount of approximation there. So my m sub yi is approximately equal to, and now what we're going to do is put the x bar first, and then the rest of this jazz. And then I'll just put in what this is equal to. This is 1/2 x sub I minus 1 plus x sub I over 2. So then my my total moment, would be approximately equal to the sum of all these things. I don't know why I put the over 2 in there again. Would look like this. So this is where we've got it using our approximations and machinations here. Now what's going to happen as the norm of the partitions go to 0? Well, x sub I minus 1 is going to go to x sub I, right? Which means that my x sub I bar is going to go to 1/2 x sub I plus x sub I, which is 1/2 of 2xi, which is xi, right? That's a fancy way of saying that when those subintervals, as they get smaller and smaller, right, all the points are going to go to the same place, namely x sub I. So I can approximate this even more. That's approximately equal to just x sub I. And so we get down to this for our Riemann sum. So now we take the magical limit here, and what's going to pop out? Oops, a moment about the y. The moment about the y-axis is going to be the summation turns into an integral. We've chopped the interval up from a to b. What's the Riemann sum? What function are we sampling? We're sampling x times rho of x times f of x minus g of x dx. And once again, how do you want to read the integral? This is your displacement from the y-axis. This is your density, which is mass per area. And this is your area. So at the end of the day, you've got displacement times mass, which is moment. Okay. Now you do the same thing for the moment about the x-axis. What's going to be the same? What's going to be different? Well, for the moment about the x-axis, you need the what? Displacement about the, or displacement from the x-axis, which is given by the y value of that center of mass. So everything's going to be the same, except instead of having an xi bar, we're going to have a what? A yi bar. So this would be a y, oops, get that there, right color, yi bar times rho of xi times f of xi minus g of xi delta xi. Now, what was y bar? Y bar was the average of the f of x plus the g of x. Right? So this was 1/2 f of xi plus g of xi, and then all this other stuff. So what's going to happen? Take the limit as the norm of the magics go to 0, and as I flip the page, what's going to happen? The moment about the x-axis is going to be the integral from a to b of, well, 1/2 f of x minus g of x, 1 plus g of x times rho of x times f of x minus g of x dx. So once again, this is your displacement from the x-axis. That's your density, which is, once again, mass per area, and that's your area. Now we can clean this up a little bit. We can pull the 1/2 out front, integral from a to b, rho of x, and you notice what we have here, a very convenient difference of squares. And that's your mx. And so then to get your center of mass, x is your my over m, y is your mx over m. All right. Now, these formulas, I don't like to use the word ugly, but they're uglier than the formulas you're going to get in Calc 3. Because once again, in Calc 3, you're allowed to chop up the x-axis and the y-axis. So the formulas make a lot more sense. You're given a lot more freedom, too, if your density varies with y. But let's use these formulas. And let's find the center of mass of a semicircle. So here's a semicircle. We're going to do x squared plus y squared is r squared, and we want the top half. So we can take our f of x here to be the square root of r squared minus x squared, and then the g of x we can take to be 0. So this is our region. We want to find the center of mass of that. Now, if you think about it, if I gave you half a disk like this, right? We should, in a uniform density. So we're going to assume the density here is a constant. All right. So we'll write that as rho of x equals k. So to find the mass of this, I would integrate from a to b, rho of x times f of x minus g of x dx. In this case, I would be integrating from negative r to r of k times the square root of r squared minus x squared minus 0 dx, and this would just be k times the integral negative r to r of the square root of r squared minus x squared dx, which is k times the area. And we know what the area of that is, right? It's half the area of that circle. So that would be 1/2 k pi r squared. So that would be the total mass. Now, if you think about balancing a semicircle, it's symmetric about the y-axis, right? It's symmetric about the center. So you would expect that the moment about the y-axis should be what? In other words, there's just as much semicircle on the left as there is on the right. That means that the moment about the y-axis should be 0. So the moment about the y-axis is the integral from a to b, x, rho of x, times f of x minus g of x dx. So that's using our formulas there. And for our particular case, I'd be integrating from minus r to r, x, the density is constant, and then the f of x is the square root of r squared minus x squared. And once again, the g of x is 0, because it's the x-axis. And I can pull the k out front, negative r to r, x, square root of r squared minus x squared dx. Now at this point, you may want to jump in and do a u substitution, fine. But let's make an observation here. This is an odd function. If you were to graph this function, it would look like this. And I'm integrating from negative r to r. And what do we know when we integrate? What do we know when we integrate an odd function about an interval symmetric about the y-axis? The area above completely cancels out the area below. So this calculation matches our intuition that the center of mass, the x-coordinate in the center of mass, would be 0 over the mass, which is 0. So the center of mass here is going to be somewhere on the y-axis. Right? And so the question is, where along the y-axis? And that's why we need to do the moment about the x-axis. How far up and down? We know it's heavier above than below because there's nothing below it. So it should be somewhere between 0 and r. Where is it going to be? Well, let's find that out. The moment about the x-axis would be the integral from a to b, rho of x times f of x squared minus g of x squared dx. So in our particular case, we're integrating from negative r to r. The density here is a constant. The f of x squared, well, that's really going to help us out. That's going to square that square root away. Now what we can note about this is that this is an even function. Right? It's an even function. And when you integrate even functions, you can just integrate half and then double your answer. So I'll pull the k out front, double it. Make sense? And so I get 2k times. I'm integrating with respect to x. R is a constant. So that's just going to give me r squared x out of that. Minus 1/3 x cubed. We got a cat attack here. Go, buddy. Let's go over there. Just for a few more minutes. So this is 2k times, plugging in the r, gets us an r cubed here. Oh, he's messing with the wires. Come here, buddy. Minus a 1/3 r cubed minus 2k, and when you plug in x equals 0, you get a bunch of zeros. So I've got an r cubed minus 1/3 r cubed. That's a 2/3 r cubed. So I get 4/3 k r cubed. So that's my moment there about the x-axis. So to get the center of mass, the y-coordinate of that, I take the moment about the x-axis and divide by the mass. I actually have something to divide here. 4/3 k r cubed divided by the mass, which was 1/2 k pi r squared. So we got some fraction gymnastics here. When you divide by the half, you're multiplying by 2, so that would be an 8/3. You see the k's drop out. It's constant density. That'll drop out. Looks like we got an r over pi. So it's 8 over 3 pi times r. So your center of mass, x bar, y bar, would be 0, and then 8 over 3 pi times r. Great. So to balance this, that's your center of mass.